Hello, everyone. Oh, I think I have an echo. Okay. Welcome to another seminar of our seminars of the astronomy department. We are really sorry for the delay. We have a very small technical problem. Many thanks for joining us here in presence, or if you are joining us through the Google Meet or through our YouTube channel. And today we have the pleasure of having Professor Rogerio Rosenfeld with us. Many thanks, Professor, for accepting the invitation to be here with us. So for those who doesn't know him, I will just briefly give an introduction. He has a very long trajectory in his career. He got his bachelor and master degree in physics here, and physics in USP. And he got his PhD from Chicago University, followed by several postdoc positions in the US. He was, among other things, director of the Instituto de Física Teórica of UNESP, president of the Sociedad Brasileira de Física. Currently, he's a full professor at UNESP and vice director of the ICTP Institute. His research is on phenomenology of elementary particles. And today he's going to talk about cosmology with the state-of-the-art photometric galactic survey, dark energy survey, and legacy survey of space and time. So if you have questions here in the audience, I think you can just raise your hand. But the people in Google Meet and in the YouTube, is better to make the questions after. And before I forgot, today is the first coffee break here. So if you are around here at the Institute, please join us for the coffee break after, so we can discuss a little bit more with the speaker. So, Rogerio, whenever you...
Thank you, Maria, for the introduction. So when she said long career, it's a nice euphemism for old person. So yeah, so and you probably noticed that she said I'm a particle physicist, which is true. And in the last 15 years, I have drifted from particle physics into cosmology, as you will see. So I want to talk about what we're doing. So we're working with cosmology, with the state-of-the-art photometric galaxy surveys, in particular the dark energy survey, and the future Vera Rubin Observatory legacy survey of space and time. So this is actually a picture of the Cerro Tololo International Observatory, where the dark energy survey took data until 2019. And I'm also vice coordinator of this UNESP, and that's it. Okay. So I have a lot of material and 40 minutes to go. I'm counting the time, I guess. Let me do it. So, but if you have questions, please ask. Okay, I don't care if I don't finish the talk. I think the most important part is, especially the students, ask questions, please. Okay. So. First of all, maybe all of you know, maybe you don't, but there are two main types of galaxy surveys. So what are galaxy surveys? So we want to get a huge number of galaxies and do statistics with it. And there are two main types of ways of getting this, this large catalog of galaxies. One is using spectroscopic surveys, so actually taking spectra of galaxies. This is resulting in a very good quality redshift measurement. We call it spectroscopic redshift. But it's sometimes costly to take spectra of individual galaxies. So you have fiber optics, okay. So it's and also you don't have the image, you just have the spectrum. Also you have to know where the galaxies are. That's another thing I didn't say here, but you have to know where the galaxies are to put the fiber optics on top of the galaxy. The other way is doing what's called the photometric surveys. So this is a very simple idea. You just take pictures of the sky, a certain area of the sky, with different color filters. And with this information, first of all, you have this field of view full of galaxies. It's already there. You don't have to know where the galaxies are beforehand. And yeah, and the problem with this method is that you don't have a very precise redshift. You have the like a very poor spectrum because of these filters. So you get a fair quality of photometric redshift, but you can get a large number of objects, and you also have the images of the objects, not only the spectra, which is important for measuring what we call the shear. So this is the formation of the shapes of galaxies due to with gravitational lensing. This is amazing, and that can be done. So the projects I'm going to talk about today, which are a member of the Dark Energy Survey and the Galaxy Survey Space-Time, are both photometric surveys. So this is a somewhat outdated schedule of surveys, just for you to have this from 2014 is the so-called Dark Energy Task Force. You can look it up. And here you can see that they're divided into blue. So this is photometric with images, and red is spectroscopic. So of course, if you look at this is everything is late. So this is why it's outdated. And the names changed also. So if you know, the name changed in 2019, I think. So these are the instruments that we're talking about. We're talking about we're talking about the Dark Energy Survey, which actually took data until 2019, and LSST, which has not started yet. Okay, and so let me talk a little bit about Dark Energy Survey collaboration. It's an international collaboration with more or less 600, 700 participants these days. And the first director was John Peoples, second director was Josh Freeman, and we are in the third director, Rich Cron. And Brazil is part of this collaboration. So there are 25 institutions, 7 countries. And what we do, as I just mentioned, we take pictures of the sky. So we have this fantastic CCD camera with 570 megapixels called the Dark Energy Camera, which is mounted on the focal plane of a 4-meter telescope. The telescope is old. It's called Blanco telescope. This is the dome of the telescope in CTIO in Chile. So the full survey took 5.5 years from 2013 to 2019. And the results I'm going to discuss today are the results from the so-called year 3 catalogs. So data taken from 2013 through 2016. So it's a wide field survey. We cover 5,000 square degrees in the sky. So basically 1/8 of the full sky in 5 bands, up to magnitude 23. And for the year 3 catalog, we have positions and shapes of roughly 100 million galaxies. So this is the telescope, the Blanco telescope, which was totally refurbished to receive the Dark Energy Camera. Those are the CCDs. You can see a typical picture. This is enlargement of one of these galaxies here in the CCDs. So what do we why do we want to do this? So, so we want to test our understanding of the universe. So we want to test, we have a model, actually we have several models, that describes how the universe evolves from the very beginning to today, basically. So our cosmology, our cosmological models, they have to explain how the universe starts from quantum fluctuations, which are we believe in inflationary phase, so very, very early on in the universe, until galaxies today. So this is a very tall quest, okay? So, so the idea is that we have to test things that happen very early on in the universe. So this is where the cosmic microwave background was generated around 400,000 years after the Big Bang. And this is very well tested with measurements of satellites like Planck, for instance. Oh, this is, well. And then what we do in our galaxies, but then I don't see your hands up. So you want to ask a question, scream, okay? Shout. Please do ask questions. This is the important part. So we want to take our data at present, more or less, so redshifts of basically 1, and then we have to see if our model is consistent, if what describes the physics at the CMB time, or the cosmic microwave background was generated, is consistent with what we see today. So this is what we want to do. Is the late time clustering that we observe today compatible with the prediction of a model? And the model that we have is called the standard cosmological model. That's what's the Lambda Cdm model. So it's a model that has a cosmological constant and cold dark matter, and it's a flat universe. So it's a flat Lambda Cdm model. This is the simplest model that we have, and describes pretty much everything that we see today. So is this model compatible with these CMB measurements? That's the question we want to ask. So let me talk a little bit about the year 3 data of Dark Energy Survey. As I said, we already published the data from the 3 years of observations. And these are the most stringent cosmological constraints that were obtained from a single galaxy imaging survey. And combined with external data is the most stringent constraints on cosmological models overall. So, in the end, in this very simple model, we have 6 parameters. So 6 parameters basically define the standard cosmological model, Lambda Cdm. These parameters are related to the amplitude of the primordial fluctuations, so the fluctuations that are generated at inflation, what is called the spectral index of fluctuations, so how the power spectrum changes with scale. This is called NS. This is the Hubble constant. This is the quantity of matter, dark matter and baryonic matter. This is only baryonic matter, and the contributions of neutrinos to the universe. So those are the 6 physical parameters that determine the evolution of the universe. Can you believe it? That's a very simple universe. Huh? There's a catch. I'll show. But OK, this is what we want to do. So it's someone may ask, if you're paying attention to what I said, so where is the cosmological constant here? There's no cosmological constant here. Why? Because it's a flat universe. So the energy density, the cosmological constant, is 1 minus the energy density of the other components of the universe. So that's why there's no cosmological constant. And so we tested this model. So that's what dark energy survey, that's what we did. We tested this model, flat lambda CDM, to see if it's consistent with CMB, for instance, the cosmic microwave background. We also tested the next 2 simplest model. And the next 2 simplest model has only 1 extra parameter, which we call W, which is the equation of state of dark energy. So it's a constant. It's like you can think of the dark energy as being a fluid in the universe. And it's characterized by the equation of state. If it's a cosmological constant, this number is -1, -1 exactly. So we allow it to fluctuate also to see what our data can tell us about the value of this constant here, to see if there is any evidence of physics that is not in lambda CDM. Okay? As a spoiler, of course, we measure this to be -1. OK, so those are the cosmic probes that we can test within the dark energy survey, probes that test the history of expansion, like the supernova, baryon-acoustic oscillations, magnetic counterpart of gravitational waves, strong lensing, and there are probes that test the growth history of the universe, so how structure forms in the universe, how these clustering properties evolve with time, also big gravitational lensing, and galaxy cluster counts. Those are probes that gives us information about the growth of perturbations in the universe. And of course, we want to combine all these probes, OK? That's the idea. We haven't done that yet. So in this talk, I'm going to concentrate mostly in the large-scale structure, how galaxies are clustered in the universe, weak gravitational lensing, that's what we call shear, and baryon-acoustic oscillations. So it's a very, the way I described what we do, it sounds very simple, right? We just take pictures, look at the galaxies in different color filters, and study the statistics of these things and get information about the universe. It's very simple, right? The idea is simple. The details are not. So you have to, this is a slide just to show that it's not a simple thing to do. It's not a one-person job. It's a job for hundreds of people to do, OK? So it's impossible for one person to do everything. It's impossible for one person to know everything. So we start from the images, so wide field images, the deep field photometry, the selection of objects. You have to model the point spread function, image simulations, redshift calibration is a whole thing, problem blending, get the catalogs, and then you do your statistics measurements. So we measure 2-point correlation function. I tell you what this is, OK? This slide is just to show you that this is not simple, as simple as I said. The idea is simple. The details are not simple. Okay, so there are many things. And finally, you get something like this, which is the final plot that you want to show, the constraints on cosmological parameters. So yes, year 3, we had of the order of 30 papers that describes exactly these things. So I won't go into details, but I did this for fun for myself, just to show all the different papers that, all of these are papers that were published 30 papers. I think when I prepared this, there were still some preprints or to be submitted, etc. Until this is the main paper, okay? The results of what's called the 3 times 2 point analysis. And what I want you to get from this is what is the 3 times 2 point analysis. So I hope I can show you what this is. So there, just to show there are many, many things that have to be done, including simulations to test your pipelines, models, methods paper, how you're going to analyze the data, how do you measure, how do you have a covariance, this is what we participated in fact, samplers, because we need to do Markov chain Monte Carlos, etc. So there are many, many things that has to be done. And of course, photometric redshift, this is a major part of how to determine photometric redshifts. So, so we start with what is called the year 3 gold catalog. So this is this paper. So it's data from 345 nights from 2013 to 2016. And there's a way to select this, what's called the gold sample. There are several several requirements for objects to be, several cuts that we have to perform to select the objects. So we, in total, for this gold catalog, we have of the order of 319 million objects. This is the footprint in the sky, so it's not a full sky survey. We analyze a finite part of the sky, as I said, 5,000 square degrees. And these are different regions that were in the science verifications. This dark blue. Year 1 is the green one, and finally year 3 is almost the whole, it is the whole, it's almost 5,000 square degrees, see, year 3. So it's the whole thing in area. So year 6 will only go in depth and have more objects. And the gold catalog is used to produce what is called the science-ready catalog. So we have a Shear catalog, a catalog with the distortions of the galaxy shapes. And this is using a method called meta-calibration. There's a position catalog, sometimes called the lens catalog, because those are the galaxies that are lenses to galaxies in the background. And we use, there are 2 methods, actually. We have 2 catalogs. One's called Red Magic, and the other called Maglim. And then there's a third yet catalog, which is optimized to search for this baryon acoustic oscillation peak. And just to show you the redshift distributions of galaxies, I forgot to say, this is not a spectroscopic survey. I said that. It's a photometric survey. So there's uncertainty in the redshift. So we don't look in 3 dimensions because there are uncertainties in the redshift. So what we do is that we project in shells. So what we call redshift shells. So for the weak lensing, for the shear, we have 1, 2, 3, 4 shells and a catalog of 100 million objects. For the position of galaxies, we had 2 catalogs, the Maglim with 2.6 millions and Red Magic with 10.7 millions with this redshift distribution. So those are the redshift distributions that has to be convoluted when you do the projections. So I will present the DES year 3 results for 3 things, 3 times 2 point correlation functions, and our group contribute with the covariance matrix study in this part. Baryon-acoustic oscillations, and our group contribute to the harmonic space analysis and the harmonic space analysis of the shear and the clustering, which was led by our group plus Sihil Du. So this is what I want to concentrate on. This is the group I want to talk a little bit. This is Hugo Camacho. He did his PhD at IFUSP and now is a postdoc at UNESP. Maybe some of you know Felipe Andrade Oliveira. I don't know if you remember him. He was a student, a PhD student here at IAG. He was a postdoc at my institute, and now he's a postdoc at the University of Michigan. Antonino Troia did his PhD in Italy, was a postdoc in SAFER, and it's back in Padua. And Lucas Faga is a master's student at IFUSP. He's actually a student of Marcos Lima, who is a professor here at IFUSP. So let me talk about the 3 times 2 point correlation functions. I want to tell you what these things are. So what we observe are positions of galaxies in the sky, we call clustering, and also the shapes of galaxies, we call shear. So what we can do is to study the correlation between positions of galaxies in the sky. So these balls here are positions of galaxies, and these balls, these ellipses here, are the shapes of the galaxies. So these are foreground galaxies These are lens galaxies that we call, and the light, the shape is deformed by the matter between this background galaxy and what we see today. So there's a distortion, and this distortion is a measurement of how much matter there was when the light left the source to reach us. So by measuring the distortion, you have an idea of how much matter was in between. So we can have a mass map using this. So we measure correlations between the positions of galaxies and the positions of the correlations between the shapes of galaxies. So that's what we do. So and that's what is the 3 times 2 point cosmology. So this is what we call cosmic shear, so the correlation between shapes of galaxies. Again, we project in 2 dimensions. So we have redshift shells, so everything is 2-dimensional in the sky. So everything as a function of the angle theta of separation in the sky. So this is the correlation between the shapes of galaxies. This is the correlation between the positions of galaxies, so galaxy clustering. And then you can do the cross correlation between positions of galaxies and the shape of galaxies. So we study these correlation functions, 2-point correlation functions. You can actually go to higher order, but this is the simplest thing to do. And so we have 3 2-point correlation functions: galaxy-galaxy, galaxy lensing, and lensing-lensing. Okay, cosmic shear. So that's why it's called 3 times 2 points. So 3 times 2 points. So this is the result of analysis of 3 2-point correlation functions. And this is the thing that you have to understand. So and here's a plot that shows you some of the results already, but I show some more results. And this is just to introduce one quantity that we measure, and maybe you heard about it, maybe not, but this so-called S8. Have you heard of S8? Who has heard of S8? You have heard of S8. Okay, good. So I don't know, is it common for people to use S8? Because everybody uses sigma 8, which is the root mean square fluctuation of density in a sphere of 8 megaparsecs. S8 is related to that. So it's sigma 8 times a combination of omega matter to the power half, basically. So you may ask, why do we use S8 instead of sigma 8? And the answer is in this plot, because this plot is sigma 8 against omega matter. And you can see that this direction is the direction that is most constrained, has the smallest uncertainty, is this direction. And this direction is this combination. Okay? So that's why we use S8, because it's the quantity that is best constrained by our data. So most of the results will be in S8 and omega matter. So how do we estimate cosmological parameters? So this is one slide on a very simple idea and complicated to implement. Everything is simple, yet complicated. So we probably did that many times. So we want to infer the probability distribution of the parameters. So we don't, it's a Bayesian way of doing things. So it's not that we infer the probability distribution of a parameter given data and a model. Okay? So we do this using this Bayes theorem. So we have the likelihood and some priors, etc. So we need to know the likelihood, which is the data, and this enters the covariance matrix. I think I have another slide with that. And the model, you have to define a model. The model has some parameters. Those are things you want to estimate. And we have to combine measurements. There's a blinding scheme to minimize observer bias. And this is, to give an idea, the covariance matrix for this data vector is a large data vector of all their 400 elements, because it combines this 3 2-point correlation functions. Of course, I skip all the details. We have to bin in angle, bin in redshift. So there are many things that we have to do. And this is just a comparison that we made between an analytical covariance matrix from a code called Cosmology from simulations, very simple log normal simulations called Flask. And this is a covariance matrix paper that we participated. Okay, so we have a data vector. The data vector, as I said, is the 3-point correlation function. So this is the angular correlation function. This is the shear correlation function. There's actually 2 shear correlation functions, because shear has two components, and this is the so-called well, this is the galaxy-galaxy clustering correlation function. Then for each of these observables, you have to have a model that, given your cosmological model, how do you predict these quantities, and then use a Gaussian likelihood with a covariance matrix. That's why it's important, and we need to define also a prior, and from that we derive the posterior distributions of the parameters given data. Very simple, in principle. So just to give an idea, those are how do you model this 3 times 2 point correlation functions. So actually the starting point of everything is the three-dimensional power spectrum. That's the starting point of every model, is the three-dimensional power spectrum. From the three-dimensional power spectrum, so this is P of k. This is already using something called the Limber approximation, which you may or may not have heard. If you haven't asked me, I can try to explain. So you project, because this is a three-dimensional quantity, and as I said, we measure two-dimensional quantity, which depends on this L thing, on this scale. The scale is given by L, so it's a two-dimensional scale. So this is what we call the angular power spectrum. So the angular power spectrum is obtained from the 3D power spectrum by projecting along the line of sight with some selection functions, which is given by basically the redshift distributions. How am I doing time? Okay. Okay, you project this, you get the angular power spectrum, and from the angular power spectrum, you get this angular correlation functions. So you may think, why are you doing this? Isn't it easier to work with the angular power spectrum? Yes, thank you. That's the collaboration didn't do that. The collaboration used the angular correlation functions. Now our group focused on the angular power spectrum. Okay. So what are the main issues in this modeling? Of course, when I swept a lot of stuff under the rug. So we have to deal with the, as I said, there are uncertainties in the photometric redshift determination, so we have to estimate and see how to account for those. One thing that that's very important is that this is the matter power spectrum, but we don't see matter, we see galaxies. So how do you go from matter to, and also this is the total matter power spectrum. So how do you go from total matter to galaxies? That's a whole subject, okay? And it's complicated. It's not simple, Gaston. So this is called bias, called galaxy bias. And we did the simplest thing you can imagine. We just say, okay, they're proportional to each other. There's a constant, so this is called the linear bias model. It's almost, okay, I have to tell this if you're interested. So you have to define a model for galaxy bias, which relates galaxies with the matter distribution. This does not affect the shear, only the galaxy clustering. Now there's a problem that galaxies also come with intrinsic alignment. They come intrinsic aligned. It has nothing to do with the fact that there's matter intervened. They come intrinsic aligned. So there are models for intrinsic alignment that you have to take into account. And this does not affect the clustering of galaxies. Then you have to be careful with the shear calibration, which does not affect clustering. And then, of course, there are baryonic effects, which I can explain if you want. But this is the fact that the very annoying thing that the stars explode. There are RGAs with flows of matter. This is very annoying for a cosmologist, you know, very annoying. So we have to take care of these things. And also, we don't know how to do nonlinear. So everything we do is in Einstein. When you solve Einstein's equation, have you ever done that? You can do that in linear perturbation theory, no? Nonlinear, you have to rely on simulations and stuff. Or you can go to second order perturbation theory, or whatever. Or EFT of LSS. Okay, there's many things that can be done. But this is a problem. This is an issue. So there are lots of issues that we have to take into account. And so how we deal with these issues? First, because of the uncertainties, we introduce many nuisance parameters, which are meant to parameterize our uncertainties, our ignorance. And also, we devise some scale cuts. So we don't look at very small scales, because at very small scales is where these dirty things of baryon physics come in. And we don't know how to model those things. And also, at very small scales is when nonlinearities come in. We don't know how to model these things very accurately. So what do? Something extreme. We cut them out. So we are throwing data. Most of our data are thrown out. Don't blame me. It's true. Because why? Because we don't know how to model these things. So it's a theoretical challenge. It's not observational challenge. It's a theoretical challenge. So we don't know how to model, so we cut them out. Okay, so these are called scale cuts. So these mitigation methods, they have to be implemented and tested against realistic simulations. That's the DS collaboration did that. And then we require some accuracy in the recovery of cosmological parameters. That's how we test our models. So we have realistic simulations, we have our pipeline, we make all these things, we cut, we have nuisance parameters, and we recover the cosmological parameters of the simulation with a reasonable error and bias. Okay, this is to scare you a little bit. These are the cosmological parameters. So there are 7 because I also let the equation of state to be a free parameter. And you know what all these 30 parameters are? They're nuisance parameters, right? Nuisance because they are nuisance. And this reflects our certainty. So this is the galaxy bias. This was a very simple model of galaxy bias. It's a constant for each redshift beam. Remember, we have 4 redshift beams for lenses. And then there's problems with the photo Z. So you have uncertainties in photo Z. We have uncertainties due to intrinsic alignment, source photo Z, shear calibration. So these are all nuisance parameters. And guess what? We have to marginalize over them. So they enter in the analysis and we marginalize over them. So now I'm going to talk about the main results from the DES-year 3 analysis of the 3 times 2 point correlation functions. This is this paper here. And I like a lot this drawing. This is a drawing by a member of the Dark Energy Survey, Jessie Muir, who actually gave this talk on Monday at my institute. She was visiting. And I love this drawing. So this is from this dark bites. So this is light coming in. And then you take the images. And then this is great. You throw the stars out. You have to separate stars from galaxies. So you throw the stars out. And then you get all the galaxies, and you get your photometric redshift, and then you have simulations to calibrate things. Then you have your models, then you have the covariance matrix, and then in the end, that's what you get, okay? A plot like this. And this is what we do. This is the plot that we get, okay? So this is the result from the 3 times 2 analysis. Again, this is S8, so the clustering amplitude against omega matter, the density of matter. And just to guide you through a little bit, this is the blue one is just the contribution from cosmic shear. Remember, the psi plus minus is the cosmic shear. The orange one is the combination of galaxy clustering and galaxy-galaxy lensing. So this is what we call 2 times 2 in our jargon. And then finally, 3 times 2, which is the black one, which is the combination. So what you want to focus is that we reduce the uncertainties and break a little bit from the degeneracies when you combine everything in this 3 times 2 point correlation function. And those are the results. This is a factor of 2.2 improvement of signal to noise from the first year results. And these are the results S8, omega matter, sigma 8. And as promised, if you have this model which is a little bit more complicated with this equation of state which is allowed to float, you measure it to be minus 0.98 plus or minus 0.3, okay, something like that. So very close to a cosmological constant. I mentioned the cosmological constant, this number would be -1. So there's no evidence for something that goes beyond the cosmological constant. I remember when we did this analysis in year 1, we also found something like this. And the reaction of the Scott Doddleson, I don't know if you heard of Scott Doddleson, he's a member of this collaboration, was actually leading the scientific analysis. The reaction was, there goes the Nobel Prize. Okay. So something that's also interesting is that we are consistent with Planck in this S8 omega matter plane. So the green contours are the Planck results. And it's really amazing that the CMB, the physics of the cosmic microwave background is very clean, has no baryon effects, almost no baryon effects. Physics is linear. No perturbation theory works very well. So it's the best thing you can do is CMB. And the thing is that with this dirty galaxy surveys, you're not too far. In terms of, if you look at the area of this of the constraints, they're not very different. Okay. So there's a way to measure tensions. This is another topic that's very interesting. How do you measure tension? Suppose you measure one thing, gives you one set of parameters. You measure from another observable, gives another set. How do you know if they're compatible or not? There's a whole area discussing tensions. Okay. Well, we found out there's no tension. Okay, we can combine, and then we have these orange things which are very constrained. So these are the joint constraints, and these are the results on. So as you see, we get Hubble parameter, but combining everything, combining with Planck, etc. And we have a bounded mass of neutrinos, etc. And the equation of state gets much closer to -1. So we also worked on something called the baryon acoustic oscillations. Okay, I have to go a little bit faster. And this is something that we contribute a lot in the harmonic space analysis. I just want to show these are the measurements of the angular correlation function and also the angular power spectrum. So the angular correlation function has one peak, which is one characteristic scale, gives you one peak in the angular correlation function. Now, this one peak is an oscillation in the angular power spectrum. So this is something that our group did. So Hugo Camacho led this effort with these measurements and also the cosmological interpretation. I just want to show that the key result is a 2.7 detection of the BAO peak at effective redshift of 0.835, which is improved from the 4% detection, now was improved from year 1. And this is the point of dark energy. So this is the different measurements of the BAO scale as a function of redshift from different experiments and the error bars. And we are here a little bit low, but still compatible. Now I want to focus on what we mostly did, the harmonic space analysis in DES. So we have 3 papers out. This is galaxy clustering harmonic space from DES year 1, the year 1 data, with Filippi leading this paper. There is this cosmic shear in harmonic space from DES year 1, which was led by Hugo Camacho. And actually, this was accepted for publication yesterday in Monthly Notice. And this one, which is the Dark Energy Survey year 3 results from cosmic shear in harmonic space, which was led by Cyril Du. So why harmonic space? As I said, we could use either angular correlation functions in real space or angular power spectrum in harmonic space for the cosmological analysis, or there's a typo here. In principle, when there's full sky, no systematic effects, the covariances are known, etc., the information is the same, but in reality, these conditions are not met. So these are independent, totally independent analysis. The covariance matrix is more diagonal in harmonic space, so in that sense, it's more natural to work in harmonic space. But the main problem is that the footprint, the fact that we're not looking at full sky, but a finite part of the sky, introduces mode coupling. So we have to use something called the pseudo-CL method to get the cosmology out. Okay, so I'm not going to go into details. This is what we do again for the harmonic analysis, and this is the plot I sent you. In the I just want to show you this plot. So have you heard about S8 tension? Who has heard of S8 tension? You have heard of S8. Now there's a tension. People say there's a tension. First of all, the Hubble tension have heard, right? Everybody has heard about the Hubble tension. Now, what is less known is an S8 tension, but some people, especially theorists, are focusing on also the S8 tension. So this is the S8 parameter measured by different experiments, and the claim is that there's a tension between, of course, Planck and galaxy surveys. So if you look here, Planck is this orange thing here, and this is our result, okay, from DES year 3 CL. This is Shear, no? For Shear. You see that's pretty much compatible, okay? It's within errors. There's no tension within errors. And then there are different experiments like kids. It's another photometric survey. Kids, 1,000, 450. There's HSC. Okay, I don't see any tension. Some people say there's a tension. I don't see much of a tension. Anyway, so that's my take on it, that there's not much of a tension in S8. Okay? In H0 is a different thing. And we are going, that's our goal, towards a full 3 times 2 point analysis in harmonic space. So that's what we want to do shortly. So what about new physics? So right now I just told you about Lambda Cdm and very simple extension. Well, actually DS has recently published a paper on extensions of Lambda Cdm. And the extensions are this so-called W0, WA. So it's another way of parameterizing the equation of state, modify gravity, the presence of curvature, etc. This was published last month, I guess, July, and was actually co-led by Jessie Muir, this person that makes the drawing. She co-led with Agnes Fertis, she co-led this effort. Now, what I want to emphasize is that to study new models that are computationally very demanding. So, and we need high-performance computing to be competitive with other groups. So because we must run many Markov chain Monte Carlo chains with different data sets, different knowledge choices, many parameters, nuisance parameters, etc. Just to give an idea, we have a project going on early dark energy. So it's another model for dark energy, which I can tell you about. And that's in collaboration with Vivian Miranda, professor at Stony Brook, and a PhD student here in São Paulo. And that requires 100 chains, and we cannot do this without a major cluster. So that's why I asked for FAPESP for money for this, and they didn't give me. So, so we can lose competition just because we don't have computer power. OK, so in the last, how much time do I have? 2 minutes? 5 minutes. In the last 5 minutes, I want to tell you about the next thing, which is the Legacy Survey of Space and Time. So it's a 10-year survey to be conducted at the Rubin Observatory, again in CTIO. It's the next mountain, okay? It's the mountain in front of the dark energy survey, is the mountain of the LSST, using the Simony telescopes. It's a brand new 8.5 meters primary mirror telescope with a field of view of almost 10 square degrees, with the largest digital camera ever built, 3.2 gigapixels, okay? 6 times larger than the dark energy survey camera. And the construction started in 2015, and the first light is for March, first semester of 2024, and it's going to last for 10 years of survey. It's an amazing survey, lots of data, 20 terabytes of data per night. There are alerts of up to 10 million alerts per night. Data release products, okay, there are many things happening, and I just want to emphasize that one thing that's important is independent data access centers, and we're planning to have one in Brazil. So there are lots of science that can be done with SST data, much more than dark energy. So that it's not only dark energy, right? There are some unprecedented amount of data for multiple science goals. And the science topics of LSST, which actually you can see there's a whole book on the LSST science, but they are addressed within what is called the science collaborations. And they're autonomous, self-managed teams. And there are 8 science collaborations: active galactic nuclei, dark energy, informatics and statistics, transient and variable stars, Milky Way, local volume, strong lensing, galaxy solar system. Of course, the largest one is the dark energy survey, the dark energy science collaboration with more than 1,000 members. And we are participating in the LSST. There's a Brazilian participation group, which I'm the current coordinator, and Tássia Ferreira is the spokesperson. Brief history is that there was a memorandum of agreement that was signed with Brazil in 2015, which allowed for 10 PIs, and each PI can bring 4 juniors, so there are 40 juniors. And that was a memorandum that was signed by LINEA, the National Laboratory of Astrophysics, FAPESP, and RNP. And LINEA activities includes LSST and also DS. It's supported by this INCT of the universe. Luis da Costa is the coordinator, and also money from financing from FINAP. And LINEA is an institutional member of the LSST Corporation, and Luis da Costa is the representative in this LSST Corporation. So I don't want to, we got some prizes from the LSST Corporation, which allowed 2 students to go. And recently, we have an additional 15 PIs, and hence 60 juniors, because there's 4 to each, that were secured by Linea through in-kind contribution. And the in-kind contribution is at the IDAC, this Independent Data Access Center, and also contribution to the photometric Redshift effort. And they were selected through a public call, and results were announced in July 2022. And Gaston was one of the members of the selection committee. And at the moment, so we had 25 PIs and 61 young researchers in the BPG. So this is the in-kind contribution, was this light IDAC, so-called software plus data products for PhotoZ, and a pipeline scientist, which, by the way, is Sandro Vitenti, I forgot to mention. So challenges and opportunities for, from the BPGs, from the Brazilian Participation Group perspective, there are many. I won't go into details. In DESC, we want to learn about dark energy from distribution of galaxies, distribution of shapes of galaxies, supernovas, and cluster counts, which is really important. And I hope DS year 6, we also bring in cluster counts. Okay, I don't have the time. Okay, I don't have the time. There are many things that are going on in this different, these are Basilio Santiago is one PI that is working on mapping stellar populations and finding new ultra-faint dwarf galaxies. So I have a discussion about these things, but I don't have the time. Solar occultation, sorry, just to mention, okay, since I'm here. Solar occultation, stellar occultation. Stellar occultation is a big thing also with Julio Camargo leading it. This would be a revolution in this stellar occultation. They're developing a software called the Stellar Occupation Reduction and Analysis, SORA, which actually was awarded one of these Kickstart grants from LSST Corporation. So there were 15 new PIs that were selected by the BPG, 5 in active galactic nuclei, 1 in dark energy, 3 informatics and statistics, 3 in stars Milky Way local volume, and 3 in solar systems. So, so the BPG has grown recently, very recently actually. So this brings me to my conclusion. I hope I have shown to you the DS results from the 3 years of data. So this is called DS year 3. And this is a combination of correlations among galaxy positions and galaxy shapes. This is the main result from 3 times 2 point correlation functions. There's also baryon acoustic oscillations. There's also supernova results, which I did not show. These are the most precise results from imaging surveys to date. Of course, you'll be surpassed by LSST. And the results of DS year 3 are a factor of 2 improvement with respect to DS year 1. And there were no statistical significant inconsistencies with Planck found within the standard cosmological model and also WCDM. So we can combine the data to obtain the strongest constraints in cosmology. This is something I didn't say. There's some systematics that we don't understand, and we throw away some beams because of that. So the conclusion is that Lambda Cdm still is the best model, the simplest and the best model to describe the universe. No evidence of a need to go beyond Lambda Cdm so far. So there are new upcoming surveys, DESI, LSST, Euclid, and many others that will continue to test Lambda Cdm at an unprecedented level. Also forgot to mention, we are at the moment analyzing the DS year 6 data. So this is what we are doing right now, and we hope to finish in a year time, more or less. So if Lambda Cdm breaks, that will mean new physics, probably Nobel Prize. So there are exciting times ahead. So thank you for listening. I'm open to questions.
Muito,
45 minutes.
muito obrigado pela apresentação. Então vamos agora nas perguntas. Se tiver aqui. O primeiro aqui.
Please ask questions, okay?
Acho que você tem um microfone, mas o primeiro aqui.
Thanks for your talk, Rogerio. Very nice. I had a doubt, actually, when you showed the 3 times 2 correlation function point, and it's one of the first slides. Yes. No, next, yeah, this one. What you are actually measuring in cosmic shear, what is different from cosmic shear and galaxy clustering, for instance?
Thank you. So galaxy clustering, I think it's clear. That's just the position of galaxies. So it's very simple. Cosmic shear, you measure the ellipticity of galaxies. And then, so there are two directions of ellipticity. And then you say, OK, so given that this galaxy is this ellipticity, what is the ellipticity of this other galaxy separated by angle theta? So those are these are the correlation functions of the shapes of the galaxies.
Using the shape and the direction also?
Yeah, so the shape is the direction.
Okay.
The shape is related to the ellipticity.
Okay.
So there's a whole thing of how to measure the distortion, the shear. And this MagLim, not MagLim, the meta-calibration catalog is a way of, from the ellipticities to go to shear.
Okay.
It's very interesting how they do it. Actually, they take all the galaxies, they shear artificially, and then they see from the ellipticity how to get back to shear. Something like that. I didn't say it correctly, but it's something like that.
Okay. And also about the lensing, may I ask? About the lensing. I mean, you didn't talk about this here. It's just a curiosity I have. And since you are in the project, maybe you know.
Maybe.
But did you also, the collaboration, did they compute also the mass of galaxy clusters using this cosmic shear and galaxy lensing?
Yes. So I didn't talk at all about galaxy clusters. So there are measurements of galaxy clusters and trying to get cosmology from galaxy clusters. This is really exciting. And the main, so how do you do this? You have to know the cluster mass function. So you have to bin the clusters by mass and by redshift. And as you know, mass of a cluster is, first you have to find a cluster, which is non-trivial. So there are several cluster finding algorithms. But OK, suppose you find the cluster. And then how do you measure the mass? OK, so the way that was done was using richness as a proxy of the mass, calibrated via weak lensing. So in that way, weak lensing was used to calibrate the mass richness relation. So there was a measurement, and then so there was a measurement of the cluster mass distribution, let's say, and then we could get the cosmology out of this, and the cosmology was wrong. And why it was wrong? Because life, you know, but the way I tell sounds simple, but it's not simple at all. So the problem is that at low richness, there was contamination from things in the line of sight to that cluster. So the low richness clusters were not right. And that changed the cosmological analysis. Now the new cosmological analysis takes that into account. So there are many things that we only know when you do it, right? So many unknowns that became knowns. But you have to do it.
Okay, thank you.
But this is a very active, and then the other things that I'm very interested is to join cluster counts with 3x2. And this is an active area. Actually, this year one had a paper on that, led by Shunhao To, a postdoc at Stanford SLAC. And this year 3 is, we're trying to do that. One important thing is simulations, that you can use fast simulations. So this is something I'm a bit interested. We're looking with Marcus Lima and others, some sort of fast simulation for cluster counts, shear, and position of galaxies. This is not trivial, but this is important. And of course, the goal is to combine everything: supernovas, clusters, and 3x2, BAO, and get the best constraints that you possibly can.
Okay, thank you.
Thank you, Rogerio, for the talk. I have two very simple questions. One is fundamental about the lensing that you showed.
What happened to my talk?
What happened to my talk? So it's the lensing doesn't depend on the distribution of matter from the object, does it?
Yeah, of course. The lensing is caused by the distribution of matter.
Right, but does it depend on the details, or it's just the column?
So it's projected.
It doesn't depend how the matter is distributed along the. Does it?
It does, but we don't see it directly because we project it in the line of sight. But of course, in the modeling, right, we have to model it too. So in the modeling, it depends how the matter is distributed.
Right. So it's not possible to somehow, if you have knowledge about the redshifts of some sources, try to deproject this to get the distribution. Is there some way of doing this? Or?
I guess that would be possible. I haven't seen it doing three-dimensionally, you mean?
Mm-hmm.
I just saw mass maps. So those are two-dimensional maps. But in principle, yes, but there are, again, many uncertainties due to
about
the
redshift. I see.
The redshift measurements.
Right. And the second question is that if I understood... sorry. You were going
No, it's okay.
Show.
I'm just going to show this picture here.
Right.
So what you see is this, right? That's what you see, and then you can try to add, so you measure the correlation between the shapes. So, so you probably saw this. If you see a cluster, you see that the galaxies, they're deformed in a way circular. Have you seen these pictures, right? So these are weak lensing, but weak lensing are really weak in the sense that it's a few % deformation of the galaxies. So it's a very difficult measurement of this weak lensing distortion. So the shear is very, very challenging, and it's amazing that that was possible to do it. But it's sensitive to the integrated amount of matter. That these are the sources, and that's what we see. So the light starts here and goes and goes and gets distorted because of the matter, and it goes here. So what we publish are mass maps. And actually, we make cross correlations with clusters. That's interesting to see. I don't know if you saw this mass maps with clusters on top. It's very, very interesting to see. So sorry, this was the first question.
Yes. So the second, if I understood correctly, so to go from the correlations that you got from the observables to the cosmological parameters, you have to rely on comparisons with realistic simulations. Is it so?
No. No. So what you need is a good theoretical model. So let me show you this. And why do we need realistic simulation? I'll tell you why. So these things here is the theoretical modeling. Okay. The simulations is actually to test your pipeline. So the simulation is this. You take this data vector, and instead of the real data, you put some simulated data vectors, and you know the cosmology of that was put in the simulation. And then you run your, what is it? I love this drawing. Then you run this. You run this with simulated data, and you get that. But you know what the answer is. So you check if everything is okay. So that's why you use simulation. To validate.
It's to validate. Okay, it doesn't depend on the. Okay.
It's to validate the pipeline, but the pipeline has the model there. So if there's a shift here, it doesn't agree with the input, then you have to understand what is the origin of this shift. So what is wrong in your pipeline? And one of the wrong things could be the modeling. It's usually the modeling. So you're doing things where not, for instance, in scales that you're not supposed to do because, for instance, you didn't take baryonic effects into account. What I mean by baryonic effects, AGN feedbacks and things like that. We just use the power spectrum that comes out of CAMB or class, whatever these things are. And then if you look at scales where baryonic physics is important, of course your modeling is wrong, right? Incomplete, wrong. So I have to say, okay, this is wrong. So how do I deal with that? I throw this scale out. That's what we did. It's very conservative. You can do the other way. Okay, I can try to model the baryonic physics. This is a way to do it. Okay, there are ways of doing it. There's a code called AGEM code, which takes into account baryonic physics in a halo model approach. And some collaborations, not us, some other collaborations have used this code to go to smaller scales. Okay, but then you have more parameters as well, because these codes have extra parameters. And then, but again, you have to test and see if you
it's
can.
It's another purpose, the small scales too.
No, it's the same purpose, to get cosmology.
Is it possible to get information about cosmology?
Yeah. Of course, the information is degraded because you have more freedom, because more parameters. But yes, I cry every time I have to throw data out, you know. We have to throw a lot of data because we don't know how to describe them. So this is how to model them. So this is a theoretical challenge, you see. It's not the observational challenge. So this is our work.
Thank you.
Okay, I think we have a question from the people in the Google Meet, from Betch. Oi, Rochelle.
Oi, Beth.
I had a lot of fun with your talk. Thanks a lot. It was very, very nice.
Great.
So I have a couple of questions, if I may.
Of course.
One regards, okay, you said Lambda Cdm is still on.
Yes.
But you have a more constraining model that is the WCDM, right?
It's not more constraining, it's more general.
Yeah, but observationally more constraining. I mean, it can constrain better the parametric space.
No? Let me see.
Why not? Then, okay.
In WCDM, you see here, Betty, you get errors that are a little bit larger.
But at least you have W. You have cosmology.
Yeah, no, of course, it's a different model, Betty. So this is the difference. We have an extra parameter here. Doesn't mean that's more constraining. It's the opposite. We're opening up a new parameter. So we're extending the model. So in that sense,
on the other hand, you account for something that is there, right?
Okay, no. So what we do is that in the modeling, right, we allow for dark energy to be different from a cosmological constant. That's what we do. The data is the data. But in the modeling, we change the modeling, and then this is an extra parameter that enters in the modeling, goes in the Markov-J Monte Carlo, and the Markov-J Monte Carlo spits out a parameter like this. Is that clear?
This is more consistent with the dark matter, dark energy, right?
What do you mean by more consistent, Betty?
Yeah. What we might expect the existence of a W around 1 or -1.
Yeah,
right?
yeah. So we are comparing two models. In here, by construction, W is -1.
Right.
Lambda Cdm, right? Now we're saying, okay, suppose we want to test another model, a model that goes a little bit beyond Lambda Cdm. And this model is WCDM, so a constant equation of state. And the measurement gives you that is consistent with Lambda Cdm.
Right, so you cannot shift too much from Lambda Cdm.
Exactly, exactly. Of course, but Betty, yes, you're right.
It's also biased, okay, biased by the current parametric space. So it's still the best you can is this gray area, right?
Right, so this is Lambda Cdm. I don't think, I think this is the plot for Lambda Cdm, not for WCDM, I think.
Right. Oh, right.
So there's another plot like this for WCDM. I don't have it with me.
Okay, I got it then right now. Now I think it's, I got the point. Then you said you have to cut scales.
Yes.
Because you don't know how to deal with most of data.
Yes.
But you do this, I mean, consistently, in a consistent way.
Yes.
With this angular power spectrum.
Yes.
So exactly what I mean is, how do you cut this information?
Yes.
It's in scales.
Yes.
Do you use the angular power spectrum for this?
Yes.
And what is the information encoded in the angular power spectrum that you did not have before, for instance, in the two-point correlation function,
right.
or okay,
right.
And S9, S8 rather than this other parameter that depends on sigma 8.
Yes.
So, okay.
Yes. No, those are great questions, Betty. So the amount of information in principle is the same if you look at the angular power spectrum or the angular correlation function. However, the systematics are different. The covariance matrix is different. The analysis is different. But the amount of the information should be at least compatible. Okay, you can even combine them. We did that for the BAO paper. So it's a complementary analysis in that sense to the main DS. So what we did was not the main DS analysis. The main DS analysis is the angular correlation function. Okay, so then there's the question I want to ask you in a little bit more of detail is how do we make the scale cuts? And that's really important. So what we do, Betty, is the following. we generate what we call contaminated data vectors. So what are contaminated data vectors? Data vectors that contain, for instance, baryon physics. And we give this contaminated data vector to Jesse's plot. Where is Jesse's plot? To this thing, to this machine. Instead of the real
this
data,
is not there.
Yes, instead of giving real data, we give mock data, but the mock data is contaminated by baryon physics. And then we run our machine and then say, oh, wait, this thing is wrong, because I know the cosmology in the mock data, and say, oh, we get the cosmology wrong. And then what we do? Okay, so we cut some scale until we get this thing right.
Right.
From the contaminated data vectors.
Right.
That's how we do the scale cuts, and that's why you need to run many Markov chain Monte Carlos in order to find what the scale is. So there's a measurement, delta chi. There's a chi-square delta difference of chi-square when you cut the scales, and there's a criterion of stopping at some point. Okay, this is precise enough. That's it. That's how we do it, the scale cuts.
Right, but do you get a hint from what, because you know, when you throw away stuff, you get to keep on you know, a track of what you are doing, because then you know how to interpret what you get. So do you have an idea of if there is a systematic for this stuff that you threw away or not?
So
because
yes, I should have showed you. Let me show you, maybe. Yeah. So what we do is, like, for instance, in a plot like this, I don't have the real plot, but in some plots like this, you just say, okay, it scales below 1 degree. I'm giving an example, right? I don't trust. So I just use for my data vector, the real data vector, just the points that are above, let's say, 1 degree, okay? So I throw, in this case, I throw these first two beings out, these two beings, these two beings, these two beings. So that's what we do.
Right.
Okay? So it's as simple as that, Betty. There's no magic. This is really simple. I mean, to get the scale, everything is simple, right? But this is what, to get this is complicated. But that's what we do. We cut some, we say, if you cut the scales, you run that, you run your pipeline, and you see there's no difference. You run your pipeline on contaminated data vectors, and you see that you can recover the cosmology with a reasonable accuracy. So you cut the scales out. If you keep the scales, you cannot recover the right cosmology, because the modeling is not accurate at very small scales.
Right. Okay, but at least you know exactly what you are cutting, right?
We know exactly what we're cutting, Betty.
Right. Yeah. And
Trust
then
me on that.
To think about all this stuff that you put under the carpet eventually might be important.
We would love to keep all the scales, but then you need a better modeling.
Right. Mm-hmm. Makes sense. Mm-hmm. Okay. Oh, I have another question. Last question, if I may, because you mentioned this work too fast that you did on BAO, the baryonic, the baryon oscillation, acoustic oscillations. But then, for instance, we have, which is here, by the way. But then you, for instance, there is the project, you know, Brazil is very much committed with the bingo, you know.
Yes.
And you know all these people?
Yes.
And, is there any interest? I mean, is there any people from bingo involved in these efforts in the dark energy survey group, in this collaboration specifically, or not? Or you guys
not in the S, but we're talking to Alex all the time. And actually, I wrote a thematic project which was refused at the moment. I still have to.
The one for the computer.
Group. But that includes cross correlation with bingo.
Right.
Alex is part of the project.
Okay. Yeah. So it's a small.
So if you are the referee, please approve it.
No, you know, Unfortunately, I'm not of this project because otherwise, of course, I would.
I'm joking, Betty. I'm joking. It's a joke.
No, it's fine because I'm also very worried about all these cuts that FAPESP is doing with the projects. With the budget of the projects, we are all in the same ship.
Okay.
getting desperate with the lack of money. Yeah, but okay. Thanks a lot, Rogerio. I will go downstairs just to say hello
Coffee.
because
There's
I have
coffee.
to teach in a few minutes. But I'll go downstairs.
Okay. See you soon.
Coffee break and see you. Say hello in person.
Okay.
Nice.
Okay, so let's finish. Thank you very much again for this excellent talk.
You.
So I invite everyone who is here in person to meet at the coffee break and to continue with the discussion. Thank you so much.
Absolutely.